Hi. Hello, everyone. Welcome to session 6 of the Intro to AI Driven Science on Supercomputers. Today, we're going to have a talk from Huihuo Zheng, who is a computational scientist here at Argonne. But before we jump into Huihuo's talk, I wanted to share a little bit more information about the internships that I've sort of been teasing throughout the series. So with that, I'm going to share my screen for a very brief presentation that anyone, as you have questions, obviously feel free to drop them in Slack or unmute as you will. But I just wanted to let y'all know a little bit more information about this. So at Argonne and at any of the Department of Energy National Labs, we have internships that run both during the spring and the fall, but primarily during the summer. And as far as what these internships mean, some of you have potentially heard of like research undergraduate experiences that you can do. It's very similar to that. These internships are really, really exciting. They're for both undergraduates and graduates because one, you can potentially apply some of the things that you're learning now today during this series in real life to actual research that you're doing at one of these national labs. You also can have professional experiences working in a slightly different place than something that you might find in academia. National labs have a little bit of a different vibe, I think, in the best way possible. But you'll be able to experience that and also practice a number of professional experiences like communication. Additionally, you'll be able to build a network of peers. We have interns that come from across the country that can come and do internships here from across a number of different disciplines, not just in computation. And we make sure that you are able to actually like interact and socialize with each other. And along with that, I think there's this idea of building a science identity and going to a place and building experiences and confidence in your ability to do science in really, really interesting situations. So I'm going to give you a few details on a couple internships. There's more information online that I pointed you to, and all of these slides will be available after this talk. So the two main ones for undergraduate internships are SULI, which is the Science Undergraduate Laboratory Internship, and then CCI, which is the Community College Internship, which is obviously targeted at community college students. The one that you would probably target now, the applications for summer have just opened. They opened last week and they close in January. It's a 10-week program, and you can apply up to apply at 2 different DOE national laboratories. I don't know if you remember, but there are 17 across the country. So you could apply to Argonne, but if you're like interested in going to Long Island for a summer, you could also apply to Brookhaven, or if you wanted to go to California, you could apply at Lowndes Berkeley National Labs. It's a paid internship, which I think is an important piece. You get paid a stipend of $650 a week, plus housing. If you come to Argonne, we actually have housing on site that you could stay at. And for these internships, you apply and then you match with a mentor within a field that you're interested in and sort of go from there. We also have Argonne-specific internships that are funded by Argonne. We have the SIPs, which are seasonal intern programs. Again, similarly, summer programs are 10 weeks. This is only at Argonne, so if you want to come work here. Similarly, you get a paid stipend of $650 a week, and you can conduct research with a scientific team on a number of different projects. The applications for these are going to open in November, and then they will close next February. So lots and lots of time. And then again, we have on-site housing, which is exciting. And both of these, the SIPs and then the SULI and the CCI, all of these are targeted specifically at undergraduates for the most part. We also have graduate student internships as well that I can point you to towards more information. As far as eligibility, I think a really important question is like, do I have to be a US citizen? The answer is no, you just have to be at a US institution. So a US citizen or legal permanent resident. So if you're at a US school, then you sort of fall into that category. And there's because we are the government, there are drug tests if the appointment is in person. So something that's just sort of a general overview of those internships. And you can also potentially, there's a flexibility in these. They're generally 10 weeks, but they can be plus or minus whatever works within your schedule as well. So here are a few resources as far as where you can find more information, both for undergraduate, graduate, and just general DOE programs for students. So with that, I will stop. I don't know if anybody has any questions specifically right now. Obviously, feel free to reach out to me on Slack if you have any specifics. Right now, I think so mentors, including folks like Huihuo, put out specific projects that they want people to work on. I think those projects are still potentially in the works, so I don't have all of the details. And I think a lot of the things that you've heard about in these past few weeks are within the realm of possibility. So if you're like, I'm interested in doing, learning more about this specific program, this specific scientific field using AI, there's a good chance that there's an opportunity to sort of dive deeper into that as well. Cool. So with that, something that I also was in sort of the intro slides that were rolling through as people came in, something that we're hoping to do right now. ALCF has a big communications department, and we write articles on things that we do, including trainings, specifically student trainings for you. So if anybody wants to potentially be interviewed for an article that would be written for ALCF, please let me know, reach out to me here or on Slack, and I can give you a little bit more information on that. We would just mostly want to ask about your experience and sort of why you decided to do this series, how it's gone, and maybe what you hope to do with the information moving forward. So let me know, ping me on Slack or on Zoom, and I can answer more questions about that. Okay, so now that I've talked for about 10 minutes, I will pass the baton over to Huihuo. So as sort of the framework for what we're doing today, Huihuo is going to start by first talking about supercomputers and parallel AI training using a lot of the same data networks that we've been seeing for the past couple of weeks. And then we're also going to have a science speaker, Miriam Ngom, who is going to talk about her work on targeted adaptive design at Argonne as well. So with that, I'll pass things over to Huihuo and we can get started from there.
Thank you, Paige. Good afternoon, everyone. To apply for the internship, Argonne is a wonderful place to work. You have a wonderful staff to work for very cool science project. So today we're going to talk about primary parallel AI training. But I saw the title. It's called Supercomputers and Parallel AI Training. I prepare mostly for the parallel AI training. I didn't prepare that much to talk about the supercomputer. So, but I can quickly talk about the supercomputer. I have some slides that I prepared previously, and just show 3 slides about why do we need supercomputer. Okay, so let me see what I can show in the right screen. Yeah, I think I'm showing the right screen. I want to start with the evolution of computing. This slide some of the slide will be like in Chinese because I was preparing for a Chinese audience, but I will explain in English. And so if you consider, if you know a little bit history, people want to use some tool to help us to do computing, right? Right now, I'm teaching my son who is 5 years old to teach addition, like 3 plus 5. I will have to use a three finger plus 5 finger, and then my son will count it and add it up to total into 8 finger, right? But we'll quickly run out of the finger to use. So the figure show here is some kind of like a chopstick style. So if you know, some Asian people use chopsticks, and basically one chopstick will be 1, 2 chopsticks will be 2. So kind of like you have more fingers, so you can count. So this you can call it calculating chopsticks, whatever, you know. And then the other two, the middle one, I don't know how to call it in English, you know, in Chinese, it's a kind of, it called calculating plate. You know, so you have basically upper panel, you have 2 of these things, and then lower panel have 5, and then you can do addition, subtraction, multiplication, division. And when I was young, like, you know, in elementary school, we were taught to use this kind of calculating plate. And some people can do this things very fast, you know, and they can, their hand, it was so good, flipping things. And then later on, of course, in the Western countries, they invented this calculating called ruler, which I won't go into too much detail. It can do more complicated calculations. Even you can do square root, you know, by sliding this 2 ruler together. If you're interested, you can search Wikipedia. You know, it's quite amazing that people invent all these kind of things. And then later on, in the probably 17th century, there are scientists or mathematicians invented mechanical calculators. The one here is for addition, you know, adding and subtraction, and it's invented by a mathematician called Pascal, or also physicist, right? Pascal is a unit of the atomic pressure, so you know that it's a physicist. So he invented this mechanical calculators. Then later on, this only can do addition and subtraction, but then Leibniz, a mathematician, invented another more complicated calculator which can do addition, subtraction, multiplication, division. There's 4 types of calculation. Sorry, Leibniz is a mathematician, which I know many of you undergrad students, you are taking calculus, and maybe you struggle with the calculus. Calculus was invented by Leibniz and Newton, you know, and they fight with each other who invented first. But basically Leibniz, it's a very famous mathematician. So he is also a genius in inventing this calculator. Of course, later on come to the computer, right? In 1946, there is the first computer, ENIAC, was invented. It was very big and occupy a big space. I don't, if I remember correctly, it was the weight of the whole computer was 30 tons. Yeah, I might be wrong. My memory is not accurate enough, but you can check on the website. And later on, there are many generations of computers, you know, made up by different kind of fundamental units, which I won't go into details. And now what you have, everybody has, you have the laptop, you know, tablet, and iPhone, or other computing things, right? These are much more powerful than the calculator, than the supercomputer, than the computer we have in 1946. Of course, nowadays, quantum computer become very popular, and there are a variety of quantum computer come up, try to overcome the limitation of the traditional computer. Of course, people just want to do things faster and faster, right? So there's a limit in this traditional computer. And so people also invented like supercomputer, and they are not quantum computer. They are like this basically in the quantum computer, the fundamental unit is called qubit, and there are fundamental unit that you can be create a qubit by atoms or superconducting materials, or even with light, which I won't go into detail. But this is still in the process. I don't know, in how many years this will become really in production, in replacing the traditional computer, right? And of course, there is some limitation of this, a single unit, single laptop, right? Because when you see the key thing about the computer is basically a CPU, the computing, or of course right now you have the GPU. No matter CPU or GPU, the fundamental unit is the number of transistors inside of the computing hardware. And as you can see, the earliest times, the number of transistors available is less than 1,000. Right, it's around 1,000, but now it's 10 to the 10. All right, and so that's why it become more and more powerful. And the reason of that is that the fabrication in the industry, the technique, it's much more advancing. The size of the transistor becomes smaller and smaller, so that you can put more and more transistor in a small area of hardware. And so right now you have the transistor, it's in the nanometer, like 5 nanometer, the smallest one, and back then we have is like in the centimeter, in the millimeter centimeter range, right? And thankful to the advancing of the semiconductor and fabrication industry. But still, a single piece of CPU or GPU can just achieve that much, no matter how much you improve. So later on, people start to consider, how about I connected multiple CPU or GPU together, form a network, right? And so they can coordinate together, do things together, right? It's just like, I was in the college, and I see many people form study group to do homework, right? To do homework. And so that hopefully that one people maybe take like 10 hours to finish all the homework, and maybe forming a study group, 10 people working together, you can finish the homework in 1 hour, right? At the end, I found like a lot of cases take longer time, and we will discuss more later on when we have the concept of parallel computing, But the goal is that we put together all the hardware, and hopefully we can work things faster, right? And so this plot is showing the supercomputer. Of course, right now the fastest one is a Frontier, which is still not in the production yet, but it's available and some people can have access. But one thing I want to mention is that actually the earliest supercomputer was in the 1990s, early 1990s. And the power of the earliest supercomputer, it's almost equivalent to the one iPhone that you have. Like this is the earlier generation iPhone. Of course, right now I have iPhone 14 or 15, right? 14 is slightly faster than that. But like your iPhone is powerful, very powerful. Now people are trying to go to the exascale, and this improvement of the computing is dramatically improved by like 6 scale, right? Like 1 million times. I think the 1 million times, I'll give you an idea about this 1 million times. Basically, if you solve this problem, solve this problem using an iPhone or the supercomputer in the 1990s. Suppose you solve that. Okay, let me backward. So suppose you use the Fugaku, the supercomputer, and then you solve the problem in 1 hour. But then you want to solve the problem with your iPhone or with the supercomputer in 1990s, how long it will take? You can calculate it on. The answer is 100 years. 100 years, right? So So that's the power of the supercomputing. And nowadays, because we have more and more CPU, GPU connected together, we can do much more things in a faster compared to the single computing hardware like iPhone, right? So this is the idea, and hopefully, this brief introduction about this supercomputer give you some idea about why we need supercomputer and how it can help. And so now what I'm going to do is to talk briefly about the parallel AI training, and later on we will really get our hands on the code, on the Python code that in the past couple of weeks we have been using. We were training the ResNet-34, right? The ImageNet dataset for classifying whether the image is a dog or a tree, right? So later on we'll work on that code. But before that, I still want to talk briefly about the concept of this, the concept of the parallel computing. And today I want to go back to the traditional, teaching and learning way. I want to do a blackboard, which I think may be easier and simple for us to understand things. Sometimes we put too much information on our brain, we quickly got lost. So we want to talk about parallel AI training today. Parallel AI training, and the goal we want to understand. Hopefully you can see this blackboard. If not, you can speak up. We want to see the concept of parallelization, right? How this parallelization can help us to do things faster, right? And then second thing, we want to learn how to modify the Python code that we have. This is for AI training. And then the third one, we want to really run the code on Theta GPU. We will have a hands-on experience on that. So this is the three goals. After this lecture, hopefully you can check whether you learn all these things. And okay, so the first is the parallelization. The concept of parallelization is not, not complicated actually. Of course, the goal of parallelization is we want to do things faster, right? Say that you have a bunch of tasks to do, and then you have one GPU. And of course, you can do just things one by one. So this is the product, after this is the output, right? The right side, this is the input, or the task, this is the output. And you just do things one by one. Now, how can we do things faster? Of course, we can make this GPU faster, the single GPU faster. The NVIDIA worked very hard to improve their efficiency of the single GPU. Initially, they have P100, and then later on have a lot of architecture like V100, for example, and then right now we have A100 on Theta GPU and Polaris. And if you check how fast those GPU are, you can think about the V100 maybe 10, more than 10x of speed up than P100, and A100 maybe about also 2 to 5x. It depends on the real workload. For some use cases, I see it become faster and faster. So at the end, from here to here, you can get maybe 20 to 50 times faster. But that's what you can get. But how about another dimension is that suppose now you have two GPU, right? How can you use this two GPU to work things faster, right? So there are two ways you can do. The first is that, okay, how about I combine these two GPUs together and work together on this single task, right? Hopefully, with two GPU, I finish this single task faster, right? So we can reduce the time per task. And this is one important parallelization called model parallelization. Equivalent later on, we will see in the machine learning context, or task parallelization, right? Basically, we divide the work in a single task, or into different pieces, and then there's a two GPU coordinate together to work on this single task. And however, there's also another way of doing things because you have 2 GPU. Okay. So potential I can do like first GPU was on the first unit, second GPU work on the second unit, right? So and somehow if the work are independent, then you can make faster, right? This is a pretty much like in McDonald's, right? People submit the order, and then if you have 1 people to prepare the sandwich, then basically it's slow. Now you have 2 people to prepare a sandwich. What you can do is that maybe the 2 people can work together on the single sandwich, that some put the meat, some put the vegetable, and then put together, and then hand it over to the customer. But maybe a faster way of doing that is that, okay, people 1 take the order 1, people 2 take the order 2, right? And because those 2 orders are independent from each other, and this is a native way of dividing the work. So this is another type of parallelization called is data parallelization. Okay, data parallelization. And because those tasks are related to the data, which we will see later on. And then in any kind of this kind of coordination or collaboration, you can say, like the parallelization, what people really care about, the 2 important things is, first is the load balancing. Load balancing, it's whether this work are equally distributed to the people in the group or not, right? So this, I talk about the study group, right? Or if the group of people doing the same project, what I found out is that mostly 1 or 2 people do all the work, and the other people just sleeping. And then at the end, the 1 or 2 people give all the solution, and then the rest of them copy the solution, right? So this is not a good way of load balancing. So people, some people do more good work, some people do less work, and eventually you cannot really finish the 10-hour work within 1 hour if you have 10 people, right? And so it needs to have a equal distribution of the work as much as possible. And the second thing is the amount of communication among all the workers, right? So this communication will always slow things down, right? This communication is exchange of data or exchange of information among the workers. And so if in a study group, you do a lot of gossip, eventually, you waste a lot of time, right? So this communication will waste time. So we also want to eliminate the communication as much as possible, right? And so then in terms of, I'll give you like 1 example how to use the parallel computing to achieve things faster. And this is a kind of very simple example. And after this example, maybe we can go to a breakout room to take a look and then play around it, And this example is calculating if you take parallel computing class, this example about calculating the pi using a Monte Carlo method is a very famous MPI Hello World program. So how we calculate pi into a very good precise number of digits, right? We know pi equal to 3.1415926, and maybe other people can memorize more, but we want to calculate this into a high precision. So the way there's 1 way to do this is that you have a square, and then suppose you drop a lot of, and then you draw a circle inside of this square. I suppose this the length of the is 1. Then the area of this the circle inside is 4 pi, right? Pi over 4. And so one way you can do is that you just put a lot of drop a lot of like sand, for example, right? You draw a box on the this figure on the ground, and then you just keep drop sand, and you can calculate the number of this maybe I change it to stone, for example, number of stones inside divided the total number, right? And this should as you drop more and more, it should become closer and closer to pi over 4, right? And this is the ratio of the area of this circle versus the rectangle. So and of course you can do just with one worker, right? It's just one worker each time drop one point, and then calculate 1 point, calculate 1 point, and until you have enough of them, and then you calculate statistical number of inside and in, and then you can know the value of pi, right? Now if you have 2 people, right? 2 people, each people can drop this point, right? So each time you become faster, right? So then what you can do is that you still total number of points. For example, if I do like 1 million, and then in I have people 1 calculate, and then people 2, right? And people 3. So at the end, you can see that basically each people doing the things on their own independently, but at the end they communicate together. They add up all of this the number of points inside this circle together, right? And then calculate together. This will be close to 4 over pi, right? So most of the time they're doing things independently, and this also kind of balance the work in a very good way, right? Equally distribute the work, and the amount of communication is very small. Only at the end they talk to each other, like how many points you get inside of how many points you get, and then they add them together, right? So this becomes very a good way of parallel computing in certain things. And so let's spend like 5 minutes to go through the code, and then we will have the breakout room to run the code on Theta GPU. So let me share the code that we have. This is on the GitHub repo that you have been using in the past few weeks. So it's on the AI science training series and number 6 distributed training. And if you click in the README page, this is the first example that I provided here, the parallel computing, the Pi example. And so the code here I provided is using MPI 4Pi, a parallel programming, the language that the software we use to do the parallel programming is MPI. So basically, you can briefly introduce this code, a bunch of model, and then you can see here, I set the total number of points. It's 5 million, right? 5 million. And then, so now I have this, we will execute this program, multiple processors, multiple CPU, and then each of them will generate, each time will generate random number X and Y as the X and coordinate and Y coordinate of the point, and then calculate the distance. Actually, this the distance, the center of this will be in origin, so the coordinate will be from 0 minus minus 0.5 to plus 0.5, right? And so you calculate the distance, and if it is smaller than 0.5, of course, it's inside this circle, right? And so each processor will run this and calculate their own number of points inside the circle. And then at the end, we do a reduction, like adding up all the points together. So this function or reduce is to do all this adding up all those points together, and then at the end we calculate the pi, and I also do the timing, right? So you can see how much time it takes if you run things on different number of processors. So okay, so we can, this code is already you can, if you have the GitHub repo already, you can do git pull protocol and then run on Theta on Theta GPU. So this is the way how you can log into Theta GPU and how to we will do things interactively. So we log into Theta and login now, and Theta GPU login now. And then this you request a compute node, and then load a modular, and this is CD to the GitHub repo directory, and then you can run. So basically here you can see we, instead of just running Python py.py, we have this MPI run, and then we specify MPI run is run the things in a parallel way, right? So, and we specify how many workers we will run this job. So 1, 2, 4, 8, right? So then each worker will run this code, will go through this code, right? And then this MPI function inside of the code will tell the different processor how they can communicate, right? In this case, the communication is basically adding up all those points together, the number of points together. And so what we're going to do right now, maybe we can have about 8 minutes break, and not break, 8 minutes in the breakout room, and then come back. You know, I will have like a couple of minutes to just check how things go here. So while we're yeah, and this is the timing and the result that I also put here. Okay, so, and I will be answering the question. If you have hit any difficulty, put that on the Slack and I will answer, and my colleague will also help answering the question.
Excellent. Okay, so 8 minutes in the breakout rooms. We'll come back, discuss things for a couple minutes, and then we'll take our full break as well. So here we go.
Okay, wonderful. So, and everyone able to run the exercise and get a result?
Yes. So I can run up to 128 processors, and when I try to run it using 250 greater than that, it was showing that it's not satisfy the number of slots requested by the application. So my question is, how what is the maximum number of processors in this training GPU?
So we actually, in this example, we only use a CPU, right? CPU, if I remember correctly, on Theta GPU, probably 64 core, or but you can have multiple process per core. They support like multiple thread, you know. So I think like running, you can try even like higher than that, 256.
Basically, I made a typo and I tried to run it using 12,000 processors, and it was showing gave that error. Yeah.
Oh, okay. Yeah, there is a maximum, you know, MPI process you can run on a single node. Yeah.
Thank you.
How fast were you able to calculate pi?
So using 128 processor, it took like 0.34 seconds.
Okay. Okay, great.
Mhm.
Yeah. So yeah, and then just you can also compare, right? As you increase the number of processors, the time decreases, right?
Yes, yes.
Because the total here I fixed the total number of points among all the processors,
Yeah.
and now if you have more processor, each worker will have like fewer points. That's why it becomes faster. So
Yes.
that's a concept of scaling. And so yeah, I think the first part is very simple, right? It's have not too much related to the AI yet. So but after the break, focus your attention. We will really do things on AI. Okay.
Excellent. Okay, so we'll do, I think, a 9-minute break now, come back at 4 p.m. Central, and then we'll come back and hear from Miriam for our science talk. All right, welcome back, everyone. So now we'll move to our science speaker. So today we have Miriam Ngom, who's a postdoctoral appointee here at Argonne National Labs in the Mathematical and Computational Sciences Division. Her background is in mathematics. And to start, I'm just going to hand things over to you, Miriam. So if you want to share your screen, you can get going.
Sure. Thank you, Paige. Let me share my screen. Do you see my screen now?
Yep, looks good.
All right. Wait. I wanted to start. All right, there we go. Okay, so hi everyone. I'm Mariam Gum. I'm a postdoctoral researcher at Argonne National Lab, and I work with Carlo Graziani. So today I'm going to present targeted adaptive design, which is a method that Carlo and I developed, and that aims at efficiently and autonomously locating control parameters that would yield a target output design within specified tolerance. So the main motivation for targeted adaptive design, or TAD for short, comes from advanced manufacturing. For example, when you do flame spray pyrolysis optimization, you want desirable particle size distributions, and simultaneously you want to have an understanding of the flame spray pyrolysis process itself. So in this example, you have 6 control parameters to tune. So these are the type of problems that TAD aims at solving. So I'm going to present that through an example, namely atomic layer deposition. So atomic layer deposition is a thin film deposition technique. And here in particular, I'm gonna talk about ALD reactions that involve 2 chemicals, precursor 1 and precursor 2, that react with a substrate on a surface cyclically in a sequential non-overlapping manner. In particular, each cycle is comprised of 4 sequences. You have a first dose period T1, during which the substrate is exposed to the first precursor. That dose period is followed by a purge period T2, during which there is no precursor exposure. Then you have a second dose period T2 for the second precursor, and a second final purge period. And this is repeated until you reach a prescribed goal. So ALD has many applications, most significantly in semiconductors manufacturing, or in the building of energy storage systems, or also in biomedical devices. So here, our goal is to have an optimal atomic layer deposition film growth with minimal precursor consumption. So there is this work by Noah Paulson and his colleagues here at Argonne that try to optimize these two targets, like namely the film growth and the minimal precursor consumption, by tuning the dose and purge times T1, T2, T3, and T4. There are also many other parameters that can be controlled, namely the temperature, the site areas, or the characteristic times for precursor evacuation and the mass changes. So you have an important number of parameters that can be tuned to give you the film growth you want and the precursor consumption you want. So what you have is a control space where you have all these tunable parameters. So here we're going to look at the characteristic times for evacuation and the mass changes, meaning that our input space size is 4. And also you have the growth per cycle. Here we're going to look at the number of, at some points in the growth per cycle curve, E points. And we have an unknown response F between the input space and the output space that is only accessible through noisy measurements. And our goal is, given a specific growth per cycle curve, can we find optimal parameters that would give us that curve? So here we have this unknown response function F that we need to find a model for. And also we need to have some optimization problem to solve to get our target. And that is exactly what TAD does. At first, TAD will place a Gaussian process prior on the unknown response function F. So a Gaussian process is a probability distribution over possible functions. It is defined by a mean and a covariance function that have some hyperparameters that you can tune to get a good model for your function. So once you have this Gaussian process model, the first thing to do is to validate it to check if it's a good model. And we do that dynamically. I'm not going to go into the details here, but we have a dynamical way of validating our model. And after that Gaussian process fitting step, we optimize an acquisition function. So this acquisition function will tell us where to make our next samples. So after we acquire the points found in the acquisition function optimization step, we update our Gaussian process model, and we repeat this until a stopping criterion is met. So we have 2 stopping criterions. The first one is success, meaning that we found our design within the specified tolerance. And the second one is failure, meaning that we have searched our space, we have squeezed out all the information we could out of our search space, and we declare failure. So TAD is a batch iterative algorithm. So if we look at this very simple example where we try to locate this green circle here, we start with some initial point here in the lower right corner of this square. And we start with an initial search region that we put here on the upper left corner of the square. And throughout the iteration, after I think this was 18 iteration, that converged near the solution. And you can see here that most of the samples are concentrated in this diagonal part of the square, meaning that we were very efficient in that we didn't waste any computation in these regions here. So one main challenge that we were faced with was that we were using Gaussian processes and they involve the factorization of a matrix. And if we use methods like Cholesky and the matrix is of size n, that scales like n cubed, which is not feasible for big problems. So here for TAD, for example, if we have data of size n and we have a number of design objectives E, our matrix will be of size E by n, E times n by E times n. And that will scale like E cubed by n cubed. So this can become big very quickly if E is large, and also, of course, if n is large. So our solution is to use GPyTorch, which is a highly efficient and modular implementation of Gaussian processes implemented in PyTorch, and which allows to train GPs efficiently with millions of data points using fast structured kernel methods. So for the work with on the atomic layer deposition, we use GPyTorch and we looked at the performance of TAD on GPU and also on Samba Nova, which is one of the AI testbed here at Argonne. So I'll show you a simple numerical example. So we are trying to find 50 points on the growth per cycle curve, and we have 4 control parameters, which are the characteristic evacuation times for the 2 precursors and the mass changes. So what we do is first we fixed all the parameters, and we run the ALD model and get a curve. And what we try to do is to recover that curve using TAD. So we start with an initial sample of 20 points, and we are looking, so at each iteration, we add 11 points, meaning 1 target point, 1 for the solution and 10 for the source region. So TAD converged after, this was a pretty quick run. TAD converged after 2 iterations, meaning that 42 points total was sampled, and the matrix was, the matrix size was 50 times 42, which is a little bit over 2000. And TAD converged to this. You can see here that the curve that TAD produced is pretty close to the target curve. And then the solution is it gave for the evacuation times, it's also close to the optimal ones, the one that to the vanilla one, if I can call it like that. And then for the mass changes, we have some differences, but it couldn't be seen in the curve. So I guess for this particular example, the characteristics time for evacuation were more important than the mass changes. So the GP fitting time for the 2000 matrix took 4.3 seconds, and the TAT optimization time took a little bit, more, 15.8 seconds, which is normal because the optimization, the objective function is pretty complicated. I didn't show it, but it's pretty complicated, and it has, in this case, at the second iteration, it's optimizing over 44 parameters, and then it involves many matrix inversions. So that is a new, efficient, and scalable algorithm specifically well suited for design problems. It incorporates a new acquisition function that balances well what is called the exploration-exploitation trade-off, which is very important for this type of problem, for Bayesian optimization problems. And it also has a dynamical model validation. And right now, as I said, we are assessing its performance on ALD and also using concrete mixing, which is also another collaboration with researchers from Texas A&M. Thank you. Let me know if you have any questions.
Thank you, Mariam. Obviously, folks, feel free to drop questions in the chat, and I'm happy to ask them. One question I had for you is, obviously within ALD, you're able to choose a number of different precursors, sort of depending on what the system of interest is.
Yes.
I guess this may have been something I missed. Like, how do you adjust for different precursors, and like the fact that like chemical interactions might be different depending on sort of what you're starting with?
Yes. So you have so depending on what you're having, of what you are starting with, you have several constraints to keep in mind. So that's why for this particular example, I look at the evacuation time, because I didn't touch, if you see, I didn't touch the pressure, I didn't touch the temperature of that, because it would have been more, it would have involved more things. So that's why I looked at this time that are like, that have easy constraints, like they should be between 0 and 1, 0 point something and 1 and stuff like that. But yeah, you are definitely right. There are many other chemical things to keep in mind. Yeah,
it's always a challenge, right? Because experimentally, there are so many things to
yes,
take into account.
Yes, and that is true.
So another question is, like, how, for you personally, or potentially for this project, do you how much interaction do you have with experimentalists in sort of like you attempting a training and then going and potentially like presenting and then like them, like continuing the cycle?
Yes. So so this is a joint work with Noah Paulson. He's at DSL and AMD. So he gave us a model so that we use that as an emulator. So it's a physics model for this ALD simulation. So what happened at first is that you see how the ALD is like done sequentially. So you have like these four sequences that don't overlap. And then let's say you want 50 cycles. That means you have 50 times 4 like seconds. And then that means if you really want to see the this curve that you are looking for, that's something that I missed at first, that they told me when I went back and presented the first thing. You have to restart. You have to restart the whole process because it's sequential. If you keep doing it, it's like after one iteration, if you had 50 and then you came back, you are going to 100 and so on and so on. So you had to restart it all the time. So it's very important that so that we have a lot of interaction, and it's very important because we need all of this. They have this point of view and this knowledge that they have on their on this ALD process that I don't have, for example. And it's very important that I talk to them so that things make sense. Like they physically make sense, and they like the experiments have to make sense.
Definitely.
Yeah.
So one question from Slack from Zachary. Zachary asked, what is the largest number of parameters that TAD is able to estimate? Do you need a lot of observations for the algorithm to work?
Yes, it depends. So so it depends on the problems you are working at. I mean, if it's a complicated problem and complex, maybe you need a lot of observations. Like for this one, it's I showed a simplified example. We just started with 20 points, which is not a lot, but then the scaling happens on the design side because I'm trying to fit 50 points. You see what I mean? So if your problem is more complex, if your input space is large and all of that, yes, you can go as, I mean, GPyTorch shares millions of parameters, so I guess you can go much bigger than this. Yeah.
Another
there's no limit here.
Yeah. So another question from the Zoom chat. Thomas asked, if I understand correctly, TAD is a way of efficiently sampling the optimal values for several design parameters in an unknown model. But you still need to tell it how many parameters to optimize, right? Or can TAD also determine how many parameters are needed for optimal control and essentially drop parameters as needed? Oh,
we are telling it how many parameters to look for. Yeah, we are telling it. Yeah, but probably there should be a way of dropping. Like for example, in this example, you saw that the evacuation times like were fitted correctly, but then the mass changes didn't really affect the curve. So maybe, I mean, that's something to explore, like doing something like that.
Wonderful. Another question, in this project, what do you think is the biggest challenge that you're sort of facing, like potentially whether it's like interfacing with collaborators or like digging in and actually using TAD, but what is the hardest part for you right now?
I would say, like, at first it took some time. It took some time to to get to understand the ALD process, like to not do things that don't make sense. Like, for example, if you don't, let's say I was looking for an optimal temperature and I didn't like put any constraint on it, maybe TAD would go into the negatives, or I don't know. You see what I mean? So it's something that talking to the specialist and like understanding how it works, understanding their model is very critical. And also the other thing is the Gaussian process fitting part. GPyTorch is somehow new and it has a learning curve to it. So it took some time also to get to GPyTorch and then putting it in, I mean, porting our code to Teta GPU and stuff like that. Yeah.
Wonderful. I think we have time for one more question. Is if anybody has anything, feel free to drop in Slack or in Zoom or unmute. If not, I'll thank you. Thank you so much for coming and speaking with us today, Miriam. This was very great. Yeah, thank you. All right. So with that, we'll hand things back over to Huihuo and continue with his lesson.
Okay, so great. So everybody, hopefully, now you have enough strength, enough attention. So if you feel sleepy, walk around, drink some water, and come back. We need a little bit kind of more info and more attention compared to the first part. So let me again share my Blackboard. So in this session, we're really going to work on the AI code. But before that, it's still good to understand the concept, how do we do the parallel computing in AI? And then later on, after we understand all this concept, the details things are kind of very simple. So as we mentioned from last time, the last session, that we have these two types of parallelization, right? Of course, there's another one which I will mention later on. But basically, the most predominant parallelization schemes and the model parallelization and the data parallelization. In model parallelization, this two GPU will coordinate together, work on the single task, right? Or processing the single piece of data, you can say. Whereas in data parallelization, each GPU work on an independent chunk of data or independent task, right? And there are, of course, some coordination among the GPU. These two different parallelization scheme have different type of coordination or communication among them. And now, if we want to bring all of this into the context of AI, how do we, either implement this model parallelization or data parallelization in AI, right? So to see that, we have to kind of see what AI is in the top level, right? So in AI model, what we have is that we have a bunch of, okay, sorry, my drawing maybe not good. And this is I want to say that it's a data, and then this is another piece of data, right? And so you have a data set here. This is a data set. Now you have model. I just say M model. Now data set you can label as S1, S2 is just a bunch of input, right? And then the model help you. You just put in this data, data, and then you make prediction. Y1, Y2 in the image that basically you just throw in an image, and then the model tell you whether it's a dog or a cat, right, or a tree or a car, and then whether this model is good enough, I have to compare with this ground truth, right? Ground truth. You just see how close it is, right? And then you calculate the discrepancy or the error. And this is the called loss function, right? So if the loss function is high, that means that your model is pretty poor, right? If the loss function value is low, then means that the model make a good, very good prediction. And inside of the model has a lot of parameter, that the weights and bias. And basically each time after you get the loss, if it is too big, then you send feedback to this model, right? You adjust the model, or specifically about adjust the weights in the neurons and bias, right? Or parameter inside of the model, right? So now, of course, this data is stored in the storage, which is hard drive, right? And all of this are done in GPU, right? CPU or GPU or any other AI testbed. So now, suppose we have two GPU, one GPU. You just put everything in this one GPU, right? And then now you have two GPU. What we can do here. Still X1, X2, and you have two GPU. Now what to do, right? So potentially you can, in the beginning, if you just want GPU training, you put the entire model inside of GPU. Now you can split the model into this two GPU, right? You split the model, And then together, still doing the same thing. You just make the prediction for x1, get y1, x2, get y2, right? The same thing as before. The only difference is that now the model is split into 2 GPU, right? So I have a picture show here. Let me put it in here. This is the model parallelization. Basically, this is I show actually 4 worker here, 4 worker, and then this is just the model are a bunch of neurons, right? And you we split them into 4 worker. So this is the type of model parallelization. Of course, immediately you know that wow, it's when the model becomes complicated, it's so difficult to partition the model in a good way. So people can kind of work on the the worker can kind of have an equal amount of work to do, right? So it's a relatively difficult. And in terms of the communication, it basically, you know, the worker 1, for example, here, after you get the output, is sent it to other workers, right? And then the rest. So there is some communication, but this communication more kind of layer neighbor communication, right? So this is kind of very similar to when you have two or 3 people solving a same problem, and this problem have maybe 3 steps, right? The first people solve the first step, and then get the output sent to the second people. The second people solve the second step, and then eventually. But the key concept here is that the 3 people solving the same kind of the same problem. And then the data parallelization is essentially instead of these 2 GPU working together, I'll just let each GPU work on independent data set, right? Data set. So you still have x1, x2. Now you get y1, y2, but it's independent, right? And of course, each of them compared to the ground truth. So, and then you get the loss. Here, the key thing is that the loss is the total loss of the data set, right? So it has to do an average. This is the communication involved, and then do the feedback, right? And so for this model parallelization, the good thing is that, okay, the data set, it's very easy to partition the work equally. Because basically we just partition the data equally, right? And the communication involved is the similar to the one that we have in the pi example, is the adding up of all the values. And specifically, in this case, will be the weights, and it will be the loss, right? And then each model update that according to this feedback, right? Okay, so a figure for this is also very simple, right? So the key thing here is that each worker have a complete copy of the model, and then but the data is split into different pieces and feed into the worker. And while they were doing the training, they have some communication, right? So this is the overall picture of this AI training. And then if we go into detail, I'll give you a recipe, right? Of course, when we get the recipe, it's kind of getting into the details. So need a little bit of your attention. So basically what we need to do, let me say same again. There are 8 steps, which I will just mention. 8 steps in modifying a Python code. I list up here and explain why it is. First is the initialize the Horovod, the framework. We will see more. Initialize is more like you form a team, find which processes are included in this work team, right? So this is a form a team. It's very, very kind of straightforward. The second one is assign GPU to each worker process, right? This is tell each person like how much resource distributing the resource, right? like a pen or pencil or computer, right? Each person have a side of a resource that they can use to solve the problem. And it's the third one will be divide the data, right? Because the data parallel will divide the data. This is to divide the task, distribute the task, right? And 4, all of these are very straightforward. 4 is this one is a little bit tricky, is scale the learning rate. So you can see I kind of gradually incorporate this machine learning terminology. Scale the learning rate. We know we have a learning rate like 0.1 or 0.0001. And then what the scale the learning rate does is that your learning rate has to scale as learning rate times the number of processor, right? In the Horovod case, it will be size, tell you how many processor, how many GPU you are using, and you scale this right. I have been asked by a lot of people why we scale this learning rate linearly, right? Okay, this is the kind of we expect if you one person doing the work, this learning rate is how fast you can do the work, right? Basically, how fast you can solve the problem in certain sense. So one person solve that in 1 hour, then 3 persons should solve that in 20 minutes, right? The learning rate should be larger, right? Because you are 3 persons learning together, right? 1 person learns slower, 3 persons learn faster, ideally, right? So this is a kind of hand-waving answer of why we need to scale the learning rate. So this is, in certain sense, it's a setting expectation. We expect, okay, if you have 3 people working together, the learning rate should be 3 times. Okay, and then the 5th one is the wrap the optimizer. This is a little, you know, a lot of detail within this machine learning. That each time when we have this feedback, remember I have a feedback rule, right? You have loss and then you have model, and then the loss kind of provide feedback to this model, and then this is the kind of the feedback is related to optimizer, how to optimize the model, how to adjust the weight, right? And so wrap this optimizer not only include this initially only include this feedback, right? But wrapping this optimizer also include the average among all the workers, right? So these two together combine as the wrapped optimizer, right? In the TensorFlow case, it will be like the so-called gradient tape, which I won't go into too detail. And then 6 is to broadcast the model. Each one have model, right? We have different GPU. But when we do the machine learning training, the model are typically randomized. So this GM model will be different from this because they have the random seed differently, right? So, but it's so important to make everybody the same. Like, so it have to broadcast. So instead of everybody start from a different starting point, the worker 0 will broadcast its model to other worker. So this is number 6. And then the rest 2 are not too kind of crucial because sometimes the people don't use that. Okay, but as I mentioned, 6 is the checkpointing. When you do a checkpointing or print out statement, right? These are the output, input, output. You have to like only one rank do it. This is typically you can do that rank 0 to do it, right? This is like you know, choosing a spokesman, right? So when you have a group of students study solving a problem, at the end people ask how to solve the problem. It's not everybody answer the questions, right? But you choose one to represent the whole group to say, so to avoid the confusion. It's very straightforward. And then average the you know, the loss or accuracy among all the workers, right? this is a key thing, is that when in parallel computing, each one only have a local copy, only see part of the data set, right? But when we have calculated loss and accuracy, we have to do the average, similar to when we're trying to update the model, we have to do the average before sending the update. Okay, so hopefully this you are not confused. But just remember, it's very simple. Conceptually, it's simple, just how you divide the data or how you divide the model, right? So here in this example, what I show here is how in the second case, the data parallelization. And data parallelization is very simple, this 8-step. And so when you are provided with the Python code, you just look for the place to modify this 8-step. And so then the next, I will just show you the example. And if you get lost from this detail, that's okay. You can always go back to check step by step. Always see things from a top level view, and just I assure you, this is very simple. It's not complicated. So and then what I want to show you now is the okay. So here is the 8-step that I mentioned. 8-step in machine learning terminology, and then the left side, below is a TensorFlow case, how to achieve this 8-step, right? The first is initialize, as I mentioned, is just form a team of processors to do the work, and then how to assign GPU to each rank, each worker MPI process, right? In NVIDIA hardware, there is a CUDA visible devices, right? This is essentially set the CUDA visible device. So each worker, each MPI process only see one GPU. You can also see multiple GPU, of course, but this you can set this accordingly. And then loading data according. This is to divide. Maybe I should change the title. Divide the data set, right? In TensorFlow, I'm not sure whether Taylor mentioned this sharding feature last week or not. So basically, if you have a TF data set object, then you can divide this data set in using the shard function. You just tell it how many partition you want to do, and then you provide the indices. So this Horovod rank is the ID for each of the worker, right? So different worker will have different indices. Therefore, they will have a different partition, different subset of the entire data set, right? To make sure that they are doing different data set. And then scale the learning rate, right? In proportional to the number of worker, because we have more worker to do things, it should learn faster. And then broadcast the model. And the good thing about this is that a lot of this code you can directly copy, paste to the sequential code. So what I have on the right side panel is the Res934 model that Corey created and Taylor also modified a little bit. And so this is the model that runs on single GPU. And I modify a little bit, but basically the same thing. So what this code, we can briefly go through this code as just define the model, right? We don't need to look into the detail, especially when you want to modify the code into Horovod. You don't look at too much detail. You just see the overall structure of the code. So this is the definition of the model, right? And at the end, I think this is calculating the accuracy, right? Basically compare Y and Y bar. Y bar is the grand truth. And then calculating the loss. Yeah, actually it is a kind of in different perspective. This is calculating the difference, and then this is calculating how many of them are getting the correct prediction. And so this is a key, one of the key functions is each training step, right? Each training step, you have the network, which is the model, the optimizer, the image, the label. Image is the X, labels are the Y, right? And so each time we just basically throw in the X, calculating the Y, and compare Y and Y bar to get the loss, right? After we get the loss, we use them as a feedback to adjust, to calculating the gradient also. Use the gradient to calculating how to adjust the network, how to adjust the M, right, to lower the loss. This is the way it does in each training step. And then each training epoch just loop over all the each training step. So each training step will take one batch of data and then process it and then adjust the model. So each epoch will go through the whole data set, right? So this is essentially the structure. So now how do we modify the code? Where should we put all these eight things, right? The first thing, the initializing Horovod, of course, should be the very, very beginning, right? This is forming a team, right? Without forming a team, you cannot start doing things. So I changed my tab to the real code. This is the Horovod implementation. This code is inside of GitHub, so you can check. I label the change as HVD1 equivalent to the first step, right? So one is initialize. You just import a modular. You can see I basically directly copy this. If you are given with the code, even in your research, then you just directly copy this, right? This is for TensorFlow. You can also have other examples for PyTorch, MXNet, for example, but you basically directly copy and do a sanity check, see whether everybody getting a rank ID and then check the total number of processors that have. So I didn't change that much. And then I do make a little bit change here is that the number of reader thread. Taylor mentioned that we can, when we do the data loading, we can do multiple thread can load the data, right? And earlier we were doing Pi example. We see that 128 degrade the performance, right? 128 if you see the Slack message. And so basically we cannot oversubscribe the thread. So if you only have one worker, then you can use the, for example, 64 thread. But now you have two workers. Each worker can only use like 32 thread at most, right? Adding up together will be 128. So that's how I actually, this should also divided by the number of processor per node instead of the total number of processor. I have to modify this, but you get the idea on this. And so this is the first step. The second step, assign to GPU to each rank. This is also should be in the very beginning, because once we know the GPU, I mean the rank ID, we can immediately assign GPU to that particular rank, right? So this is the like right after that, right? 3 is loading the data, sharding the data set, right? Dividing the data set. So what we need to do is just search the code. Where is the data loading part, right? So I think we can search. So here we have a function prepare the data loader. So yeah, so actually Taylor already wrap everything inside of this get data set. So later on, if you can check the get data set function, it has this shard function implemented already. The only difference, the only thing I make change is initially Taylor have a fake Horovod, like basically all the rank are rank 0, and then the number processor, all the rank only report 1, right? So I remove the fake Horovod and replace it with the Horovod object that we imported. And so, and you can check the get dataset function. It's another Python file. And scale the learning rate with the number of processors. And where do we put this line? It's you search for optimizer. because learning rate is specified in the optimizer. So this optimizer, you can see I multiply this learning rate here, right? And then wrap this gradient tape. And again, where do we put this? We just find where is the gradient tape. It's in the training step, right? So this is tape. So we wrap this with a distributed version. So not only just provide update, but also do the average of all the loss, right? And then this should be before applying the gradient. Applying gradient is basically trying to update, right? So this is to make sure that we average before applying the upgrade, before adjusting the model, right? So this should be right after the definition of the tape, before this, right? And then broadcast the model from rank 0. This is as soon as we define the model. Then after that, we can broadcast. I won't go into too much detail and because of the time. So I will let you to check on this this on your own, and then also check the rule checkpointing on rule rank, which is a rank 0. You see a lot like as I mentioned, when you have the NPI execute this code, all the processor will see the same code, will execute the code. And if you want certain processor to execute and other processor don't touch that, then you have to put an if statement. So for example, this if Horovod rank equal to 0, then you do the checkpointing, right? So otherwise you don't do checkpointing. Okay, so and then average, you can see the example I provide here. I won't go into detail. And this for the code I put here. And so now the rest of the time, I think what you can do is you modify the code on your own. You know, so this is the train. If you go to the folder, this 06 folder, you know, you just make a copy. This one is the sequential one, and then you copy it as a parallel and modify it. Modify it and then run it, right? Of course, I already provide the correct one, the one I modified with the underscore H Horovod, but it's a good exercise to modify on your own. Okay, so in the next maybe 15 or 20 minutes, you can modify the code. If you feel too complicated, you want to try running the code, then you can just run with the code that I provided. So again, you go to Theta GPU, request a compute node, and then do the scaling task the same way as you do when you do the Pi example. But here, this time, in the Pi example, we only run things on CPU. So you can go up to like 128 without any issue. But on Theta GPU, each node we have 8 A100 GPU. So at most you can go up to 8 GPU, otherwise you will hit an error. And then you can check the throughput. So this example, next week we will continue this large scale AI training by my colleague Sam. But today we just check the throughput. So I didn't let the training to run until convergence. I only like run 10 step. And then with this 10 step, we can calculate like how many sample it process, right? So, or how many image it processed. So this is tell us the scaling. Sorry for the line here. I basically reported the result, like 1 GPU, you can do 300, 2 GPU, you can get like 200. This scaling is not as good from 1 to 2, but then if you keep going, from 4 GPU is scaled to the 700, right? And then 8 GPU scaled to like 1300. It's kind of good scaling. Okay, so and then you can also have a way to visualize the communication. So Horovod provides a feature called Horovod timeline. If you specify this environment variable, then you can get this JSON file. I will provide later on. I forgot to provide how to open this JSON file, but basically you download a JSON file and then use your Chrome browser. Chrome timeline trace. I will provide instruction later on in this. But for now, maybe you just focus on the scaling, and I will modify the README, and later on in the evening you can put a recent change. Okay, so I will let you just play with this. You know, if you don't want to modify the code, you just want to run, you just directly go to the second step and make sure you get number. The number I get here is from Polaris. It's not from Theta GPU. So what you will be going to run, it will be on Theta GPU. So the number might be slightly off because of the different network connection among the GPUs. Okay, so I will probably just show here on this README, and you can try these examples.
So well, we have one question in Slack that
okay.
I think might be helpful for everybody that's listening right
Yeah.
now. Mukul asked, once data is sharded in this example, does it get shuffled and redistributed after each epoch, or what is the best practice?
Okay, that's a very good question. So this is related to the data pipelining. If we go back to the Z05, actually don't need to go to the Z05. Maybe we just view code. So go to the, I didn't show this data set implementation. This is done by Taylor, right? So you can see basically what it does, it builds a data set from a file list. And how to do that is that you have a file list, and let me go through it. By the way, this is the Horovod sharding here, right? Here is the sharding. So whether it's shuffle or redistributed after each epoch it depends on your definition, right? So you can see here, shard is before this file list, shuffle and reshuffle, right? So it will still shuffle redistributed after each epoch, but there is one thing is that since this is after the shard, therefore this shuffle will only occur within this subset of the data set, not the entire data set. Right? Hopefully you understand, because this is a pipelining. So what it does, right? It have a file list, and then divide the file list. And shuffle is a shuffle among the file list, right? And it's this shuffle function is after this shard. So therefore, it only shuffle among the subset. So each worker will have their own shuffling among the data set they see. Potentially, I think you can also move this shuffle, move the shuffle above this shard. Then it will shuffle the entire data set and then distribute it, Okay, hopefully that answer your question.
Yeah, thank you. So I see that we have about 7 minutes left. I don't know if that's necessarily enough time for folks to play around. I think maybe before we let people go and play a little bit, maybe clarify what homework is, just in case people need to drop off early.
Sure. Yes. So this homework, maybe it's a preparation for next week's contents. I didn't talk with Sam, much about what he is going to present. In this that data parallel training, there's one thing is that when we actually scale, run on large scale, it will have negative impact on the accuracy. So, and then especially when you go to larger and larger scale, you use more and more GPU to run, and we scale the learning rate. If the learning rate is too large, then it cannot really learn that well in the beginning. So we have to use some kind of technical warm-up epoch. And this example is a smaller example to expose this problem. The example on the ResNet 34 is kind of too large and hard to play around with. And so basically you can see this MNIX example. It runs very fast. So I was ask you to modify this. Again, the code I provided is a series code, not Horovod implemented, and you implement this Horovod code. It's very similar to the one in the ResNet 34. And then after you implement this, you run the scaling test and plot the accuracy. The accuracy will be outputted from the standard output. And then you plot the accuracy curve, like for the training and for all the validation. And then you can see like actually for 1 worker, 2 worker, 4 worker, it's okay. But if you use 8 worker or 8 GPU, then it becomes problematic, right? And then this bonus is basically, so if you set a smaller learning rate in the beginning, then you are able to solve that problem. It probably will be covered in the topic in the next week. Then you will know a little bit more detail. So basically what you need to do is to put all this PDF figure, the plot in the homework folder, and also the modified Horovod MNIX code in the homework folder, and then provide the link to this homework folder. Okay, that's I think that's all I have. Let us know if you have any questions regarding the homework submission.
Excellent. So I think what we'll do, just because we have only 4 minutes left, folks are obviously welcome, and we ask you to attempt the hands-on. And if questions come up as you go through things, both for that and for the homework, obviously just drop them in Slack, and we'll address them there. So thank you, Huihuo.
Thank you.
Okay.
Thanks, everyone.
Bye, all. See you next week.
Bye.